Okay, so the divergence theorem says that your sequence, if the sequence limit doesn't go to 0 or is divergent, then the series diverges. So what about the harmonic series? Let's apply the divergence test here. Look at the sequence. Sequence is 1 over n. So is the limit of 1 over n 0 or not 0, or does the limit not exist? So looking at that sequence of 1 over n, what's that? So he says it's divergent. The sequence is divergent. Is that right? The sequence converges to 0. So write out what this means. Let's write out what it means first, and then we'll be able to see the sequence a little better. So write out what this means. When you see this, you think what? Write it out. Andrew, did you get it? So a list? Yeah, summing them up, right? Summing them up. Okay, so this is what this would mean, summing up this list. And now looking at that list, let's apply the divergence test. What about that limit of that sequence? What about that limit of that sequence? Does it go to 0? Converge to 0? All right, so therefore, what can we conclude about the series? What can we conclude about the series? Okay, so, well, we know it doesn't not converge, right? So at least we know that, so if that didn't go to 0, then we could say definitively this series, we could stop and say this series diverges. So let's analyze this. It goes to 0, so let's analyze it. So what we want to do is we want to compare it to this series. Okay, so I've set up this series here, and then we'll compare it to this. So notice that so this right here, so if I can go 1/2 plus 1/2 plus 1/4 plus 1/4, and that equals? And then how does that compare to this? So instead of 1/3 plus 1/4, I'm doing 1/4 plus 1/4. So which is smaller? The one on the top or the bottom? Bottom one is smaller, right? You want to teach? So this is what? This is how compared to this? Because this equals 1/2 right here. And how is 1/3 plus 1/4 compared to 1/2? Greater, right? This is greater than that. Okay, and so then I've got 2 1/4. And the next here, instead of 1/5 plus 1/6 plus 1/7 plus 1/8, I'm going to take all 1/8. And when I take all 1/8, those total up to? Do you see that? And then how does my 4 things compare to 1/5 plus 1/6 plus 1/7 plus 1/8 compared to 4 1/8? Again, greater, right? Do you see that? You following what I'm doing here? So I'm going to take the next 8 terms, 1/9 through 1/16, and compare them to if they were all 1/16. And if all 8 terms were 1/16, it would equal 1/2. And how would those 8 terms added together compared to those? Again, greater, right? So what's going on here? Will I ever run out of terms that I can sum up to make a half? Now, this is going to go on forever, right? So in the next one, I'm going to take, what? 16 1/32, and that'll be a half. And then I'll take 32 1/64, and that'll be a half. So I can always do this. I can always get the next set of terms equaling up to 1/2. And so really I can show, and so this is essentially 1 plus 1/2, and I can keep finding groups that equal to 1/2. I can keep doing that. All I have to do is take twice as many terms as I did the last time, and they'll be equal to 1/2. And I'll never run out. I'll never run out of terms, so I can keep doing that. And so then, what about this series? If all of these groupings then are greater than this, what do we conclude about the harmonic series? So, yeah, what about this one this new one that I said? So obviously that's divergent, right? Because you can keep adding 1/2. Okay, and what about ours? The harmonic series is, how is its sum compared to this other one? Bigger, right? All these groupings are bigger than 1/2. And when you add the 1/2s, it diverges. Conclusion about the harmonic series? Divergent. Okay, so this is what's called the comparison test. Okay, I compared it, so I found a series that we know is divergent, and the one we were interested in, we showed that it's greater than that one, right? So if this is divergent and it's just going to get infinitely large, and we have a series that's bigger than it, it should make sense that you can conclude that that one would diverge as well. Does that make sense? Okay, so that's the harmonic series. So we know for now we've proven it. So from here on out, we see the harmonic series divergent. It's divergent. Okay, so this brings up a really important point. What did that sequence do again? Went to 0, right? Sequence goes to 0. But what happened to the series? Diverged. Okay? So what do we have? We have that if the sequence doesn't go to 0 or diverges, your series diverges. That's the divergence test. Okay? So then which series converge? Well, your sequence has to go to 0 for sure. But that's not enough, because here's a sequence that goes to 0, and we add them up, and we still have a divergent series. Okay? So which series converge? The ones whose sequence go to 0, but only some of those. Not all of them even, okay? So when you see that the sequence converges to 0, what do you say? The series has a chance to converge. It might, it may, or it may not. This is super important. This is really important. Lots of questions on the test about this one fact, okay? All right, so again, if the sequence goes to 0, conclusion about the series is maybe. Maybe this series has a chance to converge. You're telling me there's a chance. Okay? Some of you know what I'm talking about. All right. But so it's a necessary condition, but not sufficient. So a sub n going to 0 is necessary for an to converge, but it doesn't guarantee it. It doesn't guarantee it. It's not sufficient. Necessary, but not sufficient. The only way it's going to converge is if we keep adding a tinier and tinier number. But even doing that, it still could get infinitely large. We saw this before, right? We saw this before with improper integrals, right? With improper integrals, if that rate function made it to 0, then it was possible for the accumulation. It's the same thing. So it's like you can think of this kind of as the rate function, the sequence. You can kind of think of the sequence as the rate function. It's going to 0, and that is certainly necessary for when we accumulate them, when we add them all up, for it to be a finite value, but it's not sufficient. That sequence of values needs to get to 0 fast enough, right? Remember that? We talked about that before. Questions on this very important principle? Okay, so we can then look at, say, 1 over the square root of n, which is 1 over n to the 1/2. Yeah, this is it. This is new now. So this is, right, this is not the harmonic series. If it's not 1 over n, it's not the harmonic series. That's right. So what about the 1 over the square root of n? 1 over n to the 1/2. So what does it mean? Let's write it out. First term is 1 plus 1 over square root of 2 plus, etc. Okay, right? That's what this is. Does this sequence go to 0? Yes. Yes. Why? Because remember, this was our 1 over n to the p, right? That was our p sequence, right? Our p sequence goes to 0 as long as p is greater than 0. So yes, that sequence goes to 0. So what about the series now if we add all these up? Is it divergent or convergent, or do we not know? Any ideas? You have everything you need to make a conclusion. So you can know. Is it convergent or divergent? We've got that the sequence goes to 0. So we've got that necessary condition. But can we say for sure that it's convergent or divergent, this sequence? Series, sorry, series. Why?
Because the value in the denominator is, well, it increases more slow than the denominator in the harmonic series. And
Okay, so let's okay. Yep.
And from that we can conclude that if it's going to approach 0, the sequence is going to approach 0 even slower. So that means that it's not going to get to 0 fast enough in order for the sequence to converge.
Okay.
Series to converge.
That is correct. I want to get away from rate, though. Okay, so yes, you're absolutely correct. That's a totally good way to analyze it. But can we do it without talking about rate? What's that? Tell me. Yeah. Okay, so what are we going to compare? We can compare each term, right? How does 1 over square root of 2 compare to 1/2? Which is bigger? 1 over square root of 2 is bigger than 1/2, right? Because why? Because square root of 2 is smaller. Smaller number in the denominator gives you a bigger number, right? And what about these? How do they compare? This one's always going to be bigger because by taking the square root, you're making a smaller number in the denominator. So every one of these fractions is going to be bigger than every one of these fractions that we added up before. Conclusion about 1 over n to the 1/2? Divergent. Divergent because except for the first term, they're the same, they're 1, but every other term after that is greater than the terms of the harmonic. We know a harmonic is divergent. So again, by comparison, this one's even bigger. So yes, the sequence goes to 0, but each term is bigger than the corresponding terms of a divergent series, so it is also divergent. Yeah.
So if we have the form 1 over b to the n,
Good.
compare the harmonic series.
That's where I'm going. All right, good. 1 over n to the p. So we know when p equals 1, right now we know if p equals 1, divergent. And we also know if p is, what? Less than 1. P is less than or equal to 1, we know now, so 4. Why? Because we proved it for the harmonic series, and then we saw if p is less than or equal to 1, if p is less than 1, so p equals 1, sorry, p equals 1 is the harmonic series. We showed that was divergent. When p is less than 1, it's going to be a greater sum than the harmonic. So those are all divergent too. Make sense? So now the question is, what about p greater than 1? So just because we know it for p less than or equal to 1, doesn't mean we can conclude anything about, so like, say p equals 2. So here's some reasoning. Listen to this reasoning. With p equals 2, every one of my fractions is less than the corresponding fractions in the harmonic series. And because it's less than every fraction in the harmonic series, 1 over n squared is convergent. How about that reasoning? Is it good? So I'm going to say that 1 over n squared is convergent because each one of these terms is less than the corresponding terms of a divergent series. Therefore, convergent. Does it work? You should feel that doesn't feel right, right? If you've got a divergent series, you've got something less than it. What? No conclusion. No conclusion. That should feel right. You can't conclude everything. You still may have another divergent series, or it may be convergent. So that's not good reasoning. Okay. So let's talk about so let's formalize the comparison test, and then let's go back to 1 over n squared. Okay, so here's the one we used. So if AN, sequence AN series and sequence BN series are series with all positive terms. Okay, the one we're interested in analyzing is the first one, the sum of AN, okay, the series AN. We find this other series BN that we know is divergent, right? We find this other series BN that we know already is divergent, and then every corresponding term of the sequence in AN is bigger than or equal to BN for all n. Then the conclusion is that the one we're interested in is also divergent. So so for instance, we were interested in the harmonic series, 1 over n. And we came up with a series, that one that I showed you with the 1/2, right? As long as you add twice as many terms as before, you get 1/2. That was our BN. So we actually used this twice, right? We used it to prove the harmonic series, and we used it again to show that for a P series, if P is less than 1, it's divergent, right? We compared it then to the harmonic. So I want you to write the convergent version. There's a comparison test. There's like part 2 of the comparison test, which is for showing that a series AN is convergent. So what would it take to show that some series that you're analyzing is convergent by comparison to another? I want you to write it now. You write it out. Part 2. I'll give you a hint. The first line is exactly the same. So part 2. First line, same. But now we want to show that the sum of AN is convergent. Logan, you think you got it?
Yeah.
Tell me.
So let the sum of an and b and the sum of bn be series with all positive terms.
Okay.
If sum of bn is convergent and bn is greater than an for all n, then sum of an is convergent.
Right. So if we're comparing it to, if we're trying to get a convergent series, then the one we have has to be what? Convergent and greater. And then we know that ours is convergent. So if we have a convergent series Bn, and the terms of our sequence An are less than or equal to the terms of the series for Bn, then we can conclude that An is convergent. Is that what you wrote? Hopefully lots of you. So when is it that you can't make a conclusion? If you have something's divergent and yours is always less, no conclusion. What's the other time you can't make a conclusion? You have one that's convergent, and the one you're analyzing, all the terms are greater than or equal to. Jury's out. You don't know, right? You could have convergence series. You could have one that's greater. It could be convergent or divergent. But this you know for sure. So this should make sense. Okay. Check Blackboard for what the homework will be.